Good morning, people. Shubham, a very good morning. Kruti, a very good morning to you as well. Not many have joined in, is it? Am I a bit early today? I don't know. Just how many? Yeah. Saraswati, good morning. Prachi, good morning. Pratik, good morning. Anushka, good morning. Sakshi, good morning. Okay. Few more. Priya, good morning. Malvika, good morning as well. Vaishnavi, good morning. Chaitali, good morning. Sushil, good morning. Shreya, good morning. And Swapnil, good morning. Avi, good morning. I think it's Avinash, right? So, yeah, I have my basic quorum to start for the day now. I will start now. We have been speaking about Bhavika, good morning. We have been speaking about the interior of the earth and how the seismology, the studies of seismology have been important as far as knowing this. Sanchita, good morning. The various layers of the earth and what are the properties of these layers, etc., etc. And obviously, we need to come back to the surface of the earth because that is the lithosphere is our focus of study, isn't it? And when I say the lithosphere, it constitutes the ocean bed as well as the land. And when we come absolutely on the land, we actually start studying about land features. Rasika, good morning. We start speaking about land features and the study of this land features. Now, what is beneath water? If I extract all the water from the planet, like we have seen it happening as far as the documentary that we saw the other day, everything will look like land, and everything will be called as land. So everything that is above the mean sea level is going to be land, and everything that is below is going to be submarine relief. Okay, submarine because of the marine environment it has. But when we speak about geography, we have divided them separately. As I said, the that area which tends to be submerged with submarine water, marine water, is called as submarine relief, and we have different connotations for that, and that is studied in oceanography. While what comes above the mean sea level is going to be called as land, and then you have their own land features, and we're going to call them accordingly. Um, it's interesting that Rasika, good morning. It's interesting to see how we went into the study of landforms as such, because man is a land animal, we know, and knowing the philosophy, knowing the logic into studying landforms gets to be very important. Now, the presentation that I'm going to make for you all today is actually studied at PG level, but I'm purposely doing it so that I don't want all of you all to memorize and know everything, but whatever logic you can get out of it, even if you get to 20 to 25% of what we are going to do today, because the number of slides are going to be large as compared to the presentation, what is there of that, what is there in your syllabus would be not more than 30-35%. But knowing a few things, okay, and me knowing that many of you all are going in for civil services, etc., having a logic of that, you may not have geography special next year, but uh, having the logic, having the philosophy behind it, it could be easier for you all, and that's why I'm going to make this presentation today. Tomorrow, as I said, we are again going to go back to another interesting documentary, an award-winning documentary that will read into a lot of geography again. And as I did yesterday, I would be speaking about it when we go into the details of that as such. So because the presentation is longer, I would not take much of the time and immediately shift to sharing of the screen. And yeah, I would share it this way, and I want it in this way. As I said, it's a PDF one, I would have to go it this way. Now, this is a thing that we have seen earlier also. I had used this earlier, I suppose. Principles of geomorphology. What does exactly that word geo mean to us? Okay, geomorphology, the word geomorphology is has a Greek root. Okay, geo basically means the earth, and morph means the form of it, and study, of course, logy means the study it. It's literally the study of earth forms. Earth forms in the sense whatever is there on the land as such. That's very important to note that the landform events or features are going to be studied in geomorphology. What happens beneath the sea is not exactly the forte, I would rather say, as far as geomorphology is concerned. Okay, geomorphologists are concerned with the surfacial features, I would rather say, the origin, the history, the composition, and the impact on human activity, or how you, of late, of course, we speak about what is called as applied geomorphology, wherein now we see the impact of human beings on that activity as such. Okay, Earth's landforms reflect the logic, say the local and regional balance between hydrologic, tectonic, and aeolian, glacial, atmospheric, and marine processes. Okay, how all this happens is important. Okay, what is the importance of geomorphology? To understand the processes. Okay, how do we understand it? Is seen here. Okay, you'll see that. Yeah, one thing I just missed out in the earlier slide is geomorphology concentrates primarily on quaternary period. Quaternary is the most recent period. Yesterday, the commentator spoke about the latest and the severest of the ice ages after the species of mankind came up, and what happened after that is called as Holocene period. So geomorphology, it's because it's very recent, and we have traces of that around, that we look into that aspect as such. So we understand the geomorphic processes of various environments as such. The detection of natural and environmental hazards, okay, in the sense earthquakes, flooding, landslides, tsunamis, volcanoes. How are we going to detect them? Is something that we need to rather we study in geomorphology as well. Then to identify various landforms from satellite image. This is something which is, say, of course, the third point before we come to the fourth point. I have various landform features and landscape. This is visual eye. This is visual eye landscape. But many a times you'll see that what you see on your eye scale or human scale would not exactly represent what is happening. So that's why the latest of the technologies nowadays used is satellite images, and we're using satellite images extensively to identify various landforms. In fact, the theory of the meteorite hitting the earth and the dinosaurs going extinct, which we saw yesterday, was confirmed due to satellite images, because we spoke about this Yucatan Peninsula yesterday, and this meteorite collapsed on the surface, which the present site is beneath the waters now presently. As a consequence, we did not know, but once we took these satellite images, then we could see the scar of that particular meteorite hitting the surface, and that's why you'll see that we could confirm that something like that has happened, did happen at a particular point of time. Probably the reason why dinosaurs have gone extinct as such. Then coastal and river research also, not say geomorphology is not exclusively and only related to land as such, but what water does on land is also of an equal importance. So that is also something that we do in geomorphology. Vulnerability studies, say for example, with regards earthquakes, what are the areas which are vulnerable for earthquakes, and then how much would be the impact, etc., is something that needs to be done here. So vulnerability studies are there. And then it includes geology, geography, archaeology, engineering, planning, mining, construction, urbanization. All this is a part of. You can see this beautiful photograph of a dam here, and this is all comes under applied geomorphology. Okay, how are you going to apply your knowledge about this geomorphology into constructing various features? Say it goes right from roads to tunnels and to dams and canals. All of this is comes under applied geomorphology. Okay, so that is something we call as importance of geomorphology. This is something we have done just to give you a glimpse of, okay, from the Archean to Proterozoic, and then you have the Paleozoic, which has that acronym of camels often sit down. Okay, all that. Okay, now here you'll see careful instead of carefully, that's Cambrian, you have what is called as Mississippian and Pennsylvanian. This is an American diagram. You can identify that because in America you could identify two more subdivisions of the Cambrian, and that is why we name them as the Mississippian and the Pennsylvanian. Then you have the Permian, and then you move into the Mesozoic, the period of the dinosaurs. You can see towards the left, and then you have the bird taking off from here. Okay, you remember somebody did ask about it yesterday also. Then Cenozoic, modern life, and of course then you come to Holocene. And in Holocene we see human beings and how they are operating all around as such. Okay, this is the graphical representation of that. We have done this, so not going into the details of that. What past processes created this relic landscape? Okay, this rock that you can see in front of it, it's not being placed there. It has been there for, okay, possibly uh, I don't know how many centuries together as such. What modern processes are modifying it is a question that we can ask ourselves as such. Now, such ones are basically deposited by glaciers. Let me tell you, where were the processes that created relic landforms, destructional or constructional? Are the modern processes modifying this landscape destructional or constructional? These are questions which have been tasking geomorphologists of today. So that's something that's very interesting as such. Another thing that's very important is, of course, this is an American diagram. We could do the same for India also. Issue of scale. Uh, you'll see this is the geology of the Laurentian upland in interior highlands and so on and so forth. What is important for us is a classification of terrestrial geomorphological features by scale. Okay, scale. How large is it? Now you'll see that this, if you remember, I spoke about the first three orders. Okay, but there are 10 orders as far as geological features are concerned, and it represents with reference to approximate spatial scale. You can see the second column, 10 raised to 7. That's say 1 crore square kilometers. 1 crore square kilometers. 10 raised to 6, of course, 1 million square kilometers. 10 raised to 4 is going to be 10 thousands, I would say. 10 raised to 2 is going to be hundreds. And then you come down. So continents are going to be, say, the largest. And here you'll see this is the time scale. Okay, how long do they exist? Okay, so continents, of course, the longest to exist, they have been there for millions and crores and at times billions of years also. And that's why you have this 10 raised to 9 on the scale here. Okay, if you divide the continents further down, you have physiographic provinces like shields and depositional plains. They are on a lesser scale, and of course the area also, it is a few million square kilometers as such. 10 raised to 4 medium scale tectonic units, basins, mountains, etc. Okay, formed out of what can be called as external agents of erosion. Okay, their area gets lower. However, you'll see that the approximate time scale is not getting low that fast. Okay, you'll see that from the first order where the time spatial scale was 10 raised to 7, we have come down to 4. But from 10 raised to 8, which is common for the first order, we've just come down to, it still approximately remains 10 raised to 8. So on a very broad scale of time, things move very slowly for these scales as well. However, they start changing faster when we go to the fourth order, tectonic units like faults, volcanoes, etc. 10 raised to 2, that means 100 square kilometers, a few hundred square kilometers. And of course, this is going to be taking a time of a crore of years, I would rather say. Then you have medium scale and small scale. I don't want to go into the details of that. I'll post this in our group. I want you all to, those who are interested in geography, want to go into the details of these. I'll come down here. Now you'll see that this is going into minuses. Okay, from 10 raised to -1. Okay, to that's from some square kilometers. It would come down to some square in meters or centimeters or millimeters also as such. Okay, many times microscopic geomorphic processes, and these hardly take any time. Okay, you'll see that one splash of water on the surface of the ring, or one gust of wind, you'll see that the sand is carried away in different directions as such. So it hardly takes any time, particularly when you're referring to it in years. It could just go off in minutes, if not in hours as such. So this is classification of geomorphological features by scale, the size of it, and the amount of time that nature takes to hit on this particular size as such. Okay, coming to this again, you'll see that scale of landforms varies from 15 orders. We spoke only about 10. Okay, from continents to glacial striations, which could be very minute as well. Okay, age of the landforms varies from 7 to 8 orders of magnitude to a very small period of time. Larger landforms are more durable. Of course, we have seen this in the table as such. Smaller landforms created or get destroyed faster than the larger ones. As I said, a sand dune or a ripple in the river or in the desert could just change shape within a blink of an eye. Rates of geomorphic geologic change show slow for larger areas. It's something that we've already said. Now, how did people start speaking about the geomorphology? Of course, earlier when we speak about Herodotus, etc., they did speak about these things, but they had not called it as geomorphology. They were just referring to this as such. But the actual geomorphic thought started in the 1700s plus as such, okay, with Hutton, and explanations in 1800 by Agassiz as far as the glacial landforms are concerned. In fact, you'll see that the Great Lakes, which are of US, which are divided into 5 major Great Lakes today, at one point of time was all one, and that was called as the Lake Agassiz during the initial phase of meltdown of the glaciers as such. Powell, you will see, he spoke about fluvial structures, and Gilbert spoke about all surfaces. And what is interesting is about Davis. He speaks about fluvial correlations, okay, how one thing is related to other and as such. And then quantification and predictions. You see that modern geomorphology is into quantification and prediction of what is to happen to what and what happened to what was in the past as such. Okay, so geomorphology is basically land history in flashcards. Okay, things keep on changing very fast. Okay, the faster you change on speed, the faster these things happen. Now, what did Herodotus contribute? He spoke about rocks on the land in Egypt contained marine fossils, and he assumed accordingly that Nile Delta, the formation of Nile Delta, possibly has taken 1,000 years. It's not formed within a few years as such. Aristotle, he spoke about dry lands can be submerged and land can be raised from beneath the ocean. So he's speaking about plate tectonics, right? Or I would say isostasis to be so more precise, okay, and of that particular time. Then you have Senna and Leonardo da Vinci, or in the modern periods, he found marine fossils on land. Then you have Bauer, who speaks about hypothesizing that mountains are sculpted by weathering and mass movements. And then you have Steno, who speaks about water, okay, as the most magnificent agent of erosion. Then we come to Werner, and then you have George Cuvier. Okay, he speaks about catastrophic floods producing unconformities and carved in Earth's landscape and so on and so forth. Okay, but amongst them, the important one is James Hutton. Granites form through the heat and fusion deep underground and later uplifted and exhumed. Landforms are produced by a slow, continuous process. He called this as uniformitarianism. This is the most important concept a geomorphologist has to know. He speaks about what is called as uniformitarianism, because before uniformitarianism, there was a concept called as catastrophism. Let me see if I can see if there is no. Okay, we'll come to that later. Catastrophism, because you'll see that these events like volcanoes or earthquakes, which was something which happened in a small period of time, and that is why they were memorized because of the destructive effects as such. So scientists believe that everything that is happening around us is happening through catastrophes. It could be flooding, it could be droughts, it could be volcanoes, it could be earthquakes, and that whole phase was called as catastrophism. The base of geomorphology, they said, is catastrophism. Hutton says nothing like that. There is a process called as uniformitarianism. They're basically meaning that what happened as a process yesterday is happening as a process today, and will happen as a process tomorrow. Okay, the basic rules of life remain the same. The basic rules of science remain the same. They operate all throughout the times. Okay, they are uniform, and that's why uniformitarianism is the concept Hutton puts forth. He also says that there is no apparent beginning to a landform, and there is neither an end to this landform as such. This is something very interesting, which Davis later says as rejuvenation. As such. Okay, this is uniformitarianism. I'll not go into the details of that because that's beyond the scope. But knowing about this term is very important. Uniformitarianism, a basically accepted term as far as geomorphology these days is concerned. Okay. Hutton studies were followed by Playfair, okay, and Charles Lyell. You'll see that he was a very strong. Lyell was a very strong promoter of uniformitarianism, and he very categorically opposed catastrophism. Okay, and before we go further, Playfair speaks about a graded stream. It's a very interesting concept as far as river geomorphology, also called as fluvial geomorphology, is concerned, how the stream tries to grade the relief and so on and so forth. A few more of the 19th century European contributors, of them Darwin is very important. He recorded his observations during the voyage of Beagle, suggested on origin of atolls as such. Okay, how the atolls, that's a group of islands, how do they form? Okay, is how he gave us the theory of origin of atolls as such. But the most important thing Darwin did was something later, and I'll come to that. Yeah, he had his impact on this. Now, see, Darwin is 1809 and 1882. W.M. Davis is born in 1850. So by the time he's born, Darwin is 41. So he's in peak, and his theory of evolution, etc., speaking about it in a very exclusive way. Okay, and you'll see that that starts impacting W.M. Davis. Okay, speaks about evolution. Okay, because he speaks about Darwin speaks about theory of evolution. William Davis is so much influenced by his theory that he starts speaking about evolutionary geomorphology. Okay, that's an impact he had. That's Darwin on Davis, and in fact, you'll see that after Davis starts speaking about it, you'll see that he literally dominated the scenario of geomorphology for the next say a few decades as such. Okay, right up till his death in 1934. Landscape, he says, evolves in time. Stages of evolution can be determined by examining the characteristics of land, whether this is a fresh landscape, whether this is a older landscape, whether this is an adult landscape. He actually divided into names of evolution: young, young, adult, and old is how he termed landscapes into. He implied time as a critical factor in determining how lands. Okay, you'll see that if time has been very less with that landscape, it will look raw. If the time has been working on that landscape, then it will look well-developed adult. And if time has passed, significant time has passed, then of course that would look very old as such. In fact, he said that landscape, okay, and that's how it is put here, landscape is a function of structure and process in time. Landscape is a function of structure and process in time. Okay, what structures that particular landform? What are the processes operating on that particular landform? And for how much time is that process operating on that structure on that particular landform? Thus his famous statement that landforms, or rather landscape, is a function of structure and process in time. It's a very important statement as far as geography, geomorphology is concerned. Yes, he speaks about it here. Structure, what is the rock mass? Process, what is it? Constructive, destructive? We know that what comes from the interior of the earth is constructive, what comes from the exterior is destructive. And time, how much time has elapsed, okay, for a particular area, as in a particular area as such. Okay, and thus this is something that we have in our syllabus, Davisian cycle of erosion. He says that a river passes through three stages: young, mature, and old stage. Okay, that a landscape, it comes up due to constructive processes, and then destructive processes start operating on them and they start degrading the land. It grows gradually from a young, it goes to mature and eventually old. Okay, you'll see that in young, he said the valley shapes are V, and then they gradually open up into U, and then they open up gradually, very old, they open up into a very broad trough as such. Okay, a very flat plane, he says, is peneplain. And he says that this is not actually the end of it. Okay, you'll see that internal forces will again rejuvenate things, and he conceptualized the term rejuvenation as such. Okay, this is Carl Gilbert, another major name, speaks about equilibrium. Okay, then I'll not go into these because this is a bit in detail as far as equilibria, positive and negative feedbacks are concerned. And just with reference to a river, what is this? Equilibrium means a balance between erosion and deposition. Okay, the geomorphology, it refers to no net change. Usually, you remember I spoke about graded streams. Okay, it's very similar to that. Usually, in terms of balance between deposition and erosion, uplift and down cutting, or soil production and removal. Okay, you'll see that in upper courses of the river, you have more of erosion. In the middle courses, more of transportation. In the lower courses, you have a higher amount of deposition as such, is what we have to keep in mind. Uh, Equilibrium is strived for, but it's seldom achieved because equilibrium in geomorphology is a hypothetical concept. It's not something that is achieved, because the day equilibrium is achieved, remember, everything will grind to a halt as such. Okay, in fact, you'll see that you and me are breathing right now. Okay, that's basically because of an non-equilibrium between what? Between the pressure in our lungs and the air outside. When I'm inhaling air, when I inhale air, what happens is the pressure inside my lungs is low and outside is high, so it goes into that. Okay, when I exhale air, okay, the pressure outside gets lower and inside my lungs gets higher, so I come there. Now just imagine if I come to equilibrium, what is going to happen? Nothing is going to go in, nothing is going to go out. As a consequence, equilibrium would be dead. Okay, in a stage of equilibrium, a person would be dead, isn't it? And that's why equilibrium is seldom achieved as far as nature is concerned, also as such. Fluvial equilibrium, okay, recent upliftment. You'll see that how, as far as this diagram is concerned, this one, yeah, this one, 1, 2, 3, and let us see how we can relate it to this 1, 2, and 3. Very high relief. Okay, things start eroding and they get transported here, and very little of it gets transported here. Further erosion, the height goes down, and more transportation, more deposition. And you'll see that towards the old stage, mostly eroded, and you'll see that it has equalized on the land surface while it is trying to equalize beneath the ocean surfaces also. Now, there is no equilibrium between land and ocean, basically because it's not 50% land, 50% oceans. It's only 1/4 land, and in fact, it is 3/4 of oceans as such. So that's a very interesting aspect to understand what equilibrium is all about. The ultimate goal, however, is to get all of this to one level, and that is mean sea level. The base level of erosion is the mean sea level. As the mean sea level will change, it could probably lead to a resurrection of the level of equilibrium as such. So that's about it. See, this is the base level. Base level is the level below which erosion cannot occur. Okay, and above which deposition does not take place. Okay, base level below which erosion will not happen, above which deposition will not take. And that is why you'll see that deposition is more here. Yes, you're going to have it here basically because going by the basic rules of physics, but otherwise major ones has to land in the deepest of the regions as such. So that's base level. This is the graded or longitudinal profile. Okay, you'll see that this point here is the point somewhere up here, and this point here is near the mouth as such. Okay, when we speak about equilibrium, we are actually smoothing this curve. Not all rivers have so smooth ones. In fact, this is zoomed out. So if I zoom in, there could be ups and downs in the longitudinal stream profile as such. So this is stream gradient, a longitudinal one. Okay, if there is a break in that, okay, you'll see this is the normal one, and this could be some. This is an hypothetical gradient, and this could be a normal one. So you could have a fault or a waterfall here. Eventually, this is going to be eroded. What is above the line is going to be eroded, and what is below the line, this material may be deposited here. And this is very geometric. It does not happen that way, but that's an easier way to understand it. Okay, so it's going to be eroded from here. It's going to be deposited here. It's going to be eroded from here. It tends to be deposited here. You can go through the details of what is written down at your own time as such. Similarly, you're going to have coastal equilibrium. Deltas are basically attempts of coastal equilibrium, let me tell you. Geomorphic process. What exactly do we mean by a geomorphic process? The process responsible for formation and alteration of the Earth's surface is called as a geomorphic process. The physical and chemical interactions between the Earth's surface and the natural forces acting upon it produce landform. Whether it is a wind that is operating, whether it is water that is operating, is something which gets to be very interesting to know which are the processes forming that landform. The processes are determined by such natural environments as the geology, that's the rock, okay, climate, how much of rainfall is there, how much high the temperature is, how much low the temperature is, vegetation, how much is dense is the vegetation, what type of vegetation is there, and of course base level, that structure, okay, that land feature, how far away is it from the base level. If it is near the base level, the erosion will be gradual, but if it is far away from the base level, then the erosion is going to be very fast. Say for example, something near the Mount Everest will get eroded faster as compared to something very near to the Sundarbans as such. Okay, so and of course it needs to have a minimum of minimum, I would rather say naturally nothing of human interference. Okay, if you go to the Mount Everest and you start chopping Mount Everest, of course that's going to be an added thing. Okay, or you start desilting the Sundarbans, then this is going to be human interference, by the way. So let me refer to that aspect also. Geomorphic processes by definition is basically, the geomorphic processes are all those physical and chemical changes that are brought into the Earth's surface, a process by which the Earth's landforms are changed or maintained as they are. Okay, so that's an interesting thing to note. What are the agents and processes and the products? Okay, agents of geomorphic processes. These are all destruction. Howsoever you may say that river leads to formation of deltas and fertile lands, these are agents of destruction. Let me tell you. Okay, they are destructive forces. They are not constructive forces. Constructive, ironically, is a volcano, is an earthquake, basically because it develops land surfaces. Okay, so a river, a wind, glacier in polar environments, wind, a wave in the coastal environment, a river wherever you have ample amount of water to feed the channels of the river, and where you don't have a river, the wind is going to take it up. Okay, in arid environment as such. Agents, processes, and products. The process will lead to erosion, after which transportation, and that will eventually lead to deposition as such. Agents, processes, and products. Products of geomorphic processes. Okay, you'll see that deposition here. Erosion will lead to erosional landforms. Transportation actually will lead to landforms which you can't call as transportational landforms as such. You either classify them as once the material is transported, what it leaves behind is going to be called as erosional landform. Once the material is transported, where it is transported, that's going to be called as a depositional feature as such, land feature as such. Okay, and you have some of these. We have seen this earlier, if you remember. Now, what are these geomorphic processes? You're going to have terrestrial and extraterrestrial geomorphic processes. Extraterrestrial geomorphic processes are very rare. A meteor striking the Earth or a shooting star falling on the surface is an extraterrestrial process. Otherwise, most of them are terrestrial, that's within, and they are further divided into two: exogenetic processes and endogenetic processes. Endogenetic processes is folding, faulting, volcanism, earthquake, landslide, diastrophism, metamorphism. All of this is endogenetic. That comes from the interior. The forces in the interior of the Earth, they are going to produce these. But as far as exogenetic is concerned, you'll see that weathering, erosion, transportation, okay, mass movement, all of this together is called as denudation. These are destructional forces, by the way. Let me tell you, weathering is further divided into physical, chemical, and biological. Actually, biological is again a fallout of physical and chemical. Unfortunately, you don't have it in your syllabus. Had we had it, I would have gone into the details of that. But the art section doesn't have it. This very interesting aspect. It's one of the most neglected aspect, weathering and mass movement. But when it comes to impact, both of them are so very important, but unfortunately very much neglected. If we have time, sometime further down, we will go into the details of that. Okay. Here, types of geomorphic processes. Terrestrial, extraterrestrial. Let's fall of a meteorite. Okay, terrestrial processes, exogenic or endogenic, endogenous also. Extraterrestrial, here, how they are coming. Okay, meteors collapsing into, and you see that while it travels through the atmospheric layers, you see that it, because of the friction, it gets heated and it burns bright red, and that's why you feel as if a star is falling off, okay, from space. Types of geomorphic processes: exogenic or exogenous. Okay, it's as I said, equilibrium is basically a fight, or I would say it's a reaction, action and reaction between endogenic and exogenic forces. Endogenic and exogenic. It's all geomorphology is about that. Types of geomorphic processes include endogenic. Okay, you'll see that the reasons which lead to the formation of oceanic ridges, trenches, valleys, faults. You'll see that everything of this can be related to what comes from the interior of the earth. So endogenic process. Basic difference between the two processes: processes that are caused within the earth, endogenous. On contrast, exogenous processes come from the forces above the earth. Okay, endogenic processes originate from the interior. They are sudden or rapid. Exogenic originate on the surface. They're very, very slow. Erosion and deposition is very, very slow. Of course, during flood times, it seems to be faster, but majority of the period, it is very, very slow. Types of exogenic processes: weathering, erosion, transportation, deposition, and mass movement. Now, I could take mass movement and place it at the second level also, but we all know that all this happens so together with each other that it's very difficult to place them ahead of each other. I would say it's an integrated process altogether. What exactly does denudation mean? You'll see that any landscape that has come up, all the processes that act to push it down to the base level is denudation. It means that making things exposed, and in the process of pushing it down, harder rocks will stay exposed and so on and so forth. So the processes by which the rocks on the earth's surface are broken down into pieces through application of external physical forces, and the debris is transported elsewhere is known as denudation. You take it from somewhere, you erode it, you take it and you deposit it somewhere. The whole process is called as denudation. What happens in this whole process is something that has gone up, it slowly goes down. This denudational work is performed through three processes such as weathering, erosion, and transportation. Denudation, other words, is equal to weathering plus erosion plus transportation. Okay, I would add mass wasting into that. I won't agree to this slide completely as such. What is weathering? It's process in situ, where there and there only. You'll see that material does not move much, and that is why this is a unique process. Okay, and it's broken mechanically or it is broken chemically. There are two processes. Now, if life is involved in the mechanical breaking or chemical breaking, then you call it as biological weathering. That's a simple way to differentiate between types of weathering. Basically, there are only two types: physical weathering, that's or mechanical weathering, and chemical weathering. If life is involved in that, you call it as biological weathering. Of late, there is something called as anthropogenic weathering also, where human beings are responsible for that. Okay, broken mechanically into pieces, snow or frost, variation of temperature, pressure, that's all mechanical. Okay, sometimes they are dislodged by animals, that's going to be called as biological. Okay, what is erosion? Erosion and transportation are accomplished together. Okay, the process by which rocks of the earth's surface are eroded by a river. You'll see that you have rain falling here, and fine products of soil, they're going to be displaced, detached from the surface, and they're going to be displaced somewhere else also. So this is a basic process. Degradation. Okay, if you have multiple layers, one by one, the layer gets removed and the landscape gets degraded. Okay, degradation is lowering of the bottom land surface through the process of erosion. Is that something that we need to keep in mind? This is deposition. It's very similar to someone dumping something somewhere. So what is collected from somewhere gets to be deposited. Where it deposits, you'll see that it aggrades in that particular region. You'll see that you already have the larger material there. The finer material is going to consolidate in between that, and all of that is going to compact into a new form of sedimentary rocks. Sedimentary rocks are formed through deposition. Aggradation forms in where you have deposition, isn't it? Where you have erosion, you are going to have degradation. Where you have deposition, you are going to have aggradation. What started with a single layer comes to be deposited with one more layer and then couple of more layers. So it starts elevating the surfaces. Sedimentation is very similar to that. Okay, is a process by which the sediment is mechanically deposited. Okay, it becomes heavy, it cannot suspend itself, and then it gradually goes down. Okay, and it settles down, and thus you could have layers. You can see in here layers. Okay, oceanic waters as such. Mass movement is a very interesting thing, more related to human beings. As I said, one of the most less discussed processes. It's the downslope transfer of material under gravity. There is no force as such, only gravity. And whatever is transported only by gravity is going to be called as mass movement or mass wasting as such. Otherwise, it will be called as erosion and transportation. Here, if whatever gets transported only due to gravity, nobody is pushing it, nobody is responsible for it. All that is called as gravity, mass movement as such. So, if you put all of that together, what is a geomorphological process? It's this similar one that we have done. Endogenetic processes will involve folding, faulting, volcanism, earthquake, landslides, diastrophism, metamorphism. Okay, what is faulting out of it? Okay, faulting is basically when you have tension between blocks of land. Okay, you'll see that they and remember, now my hands are free, so if I put tension, they will go like this. But you'll see that I'm blocked with a lot of material around. You'll see that what happens, it goes this way, this way, this way. Okay, this is called as faulting. Tension will lead to faulting as such. It will be normal faulting, it will be reverse faulting. Okay, so a normal faulting, you'll see that it leads to increase of area. Reverse faulting, it leads to decrease of areas as such. Okay, and you could have multiple forms of faulting leading to block mountains and block valleys called as horst and grabens. Okay, an originally German term as such. Folding, instead of putting this, okay, tension, if there is compression, you'll see that if I compress these two, okay, it will lead to folds, and you have different types of folds, the anticlines and synclines. Here you have this beautiful fold that has emerged in this photograph here. Volcanism, okay, you'll see that various sources lead to say bursting of this magma into open air, falling lava, and this solidification of lava will lead to igneous rocks. The igneous rocks are also called as primary rocks. This is volcanism. This is earthquakes. You'll see that it's basically shaking of the ground surfaces. Okay, you see that you have this huge thing, that crack that has developed, but it is very similar. Now this scale is huge, let me tell you. It's and that's why it's at that particular scale, it more or looks like a river than a crack here. Okay, so that's very interesting here. You require enormous pressure for an earthquake to happen. Landslides, you see a lot of them in the hilly regions of India, right from the Sahyadris to the, so to say, the Himalayas also, the Shivaliks included in that. Okay, everything is moving only due to gravity. Nobody is pushing that. Okay, diastrophism is also called as tectonism. Another word needs to be used here. Diastrophism, also called as tectonism. Large-scale deformation of the Earth's crust through natural processes. And then you have metamorphism. Okay, a given change in due to temperature and pressure, as far as rocks are concerned, it's called as metamorphism. You have metamorphic rocks evolving out of them. Okay, and this is the final diagram. the geomorphic processes at a glance: landforming, slow, sudden changes, denudation, depositional diastrophism, earthquake volcanism, weathering, erosion, and transportation. So this is as far the whole story of geomorphology in a nutshell, I would rather say. We'll stop here and let us see if you have questions for me. I'm very sorry I cannot zoom on this particular slide, Anushka, because this is not an original PowerPoint. This is a PDF, so I did not have the um, information about how I need to go into zooming PDFs. I'll work on that. Let's see. Next time, if I'm able to, I will certainly get in that technique here also. That's all for today. If you have any questions, you could still ask me. You've done literally the whole of geomorphology in around 56 slides. Everything that you require to know on geomorphology was done. Of course, we are going to do only 30 to 35% of all that because your syllabus requires other things to be done as well. So I'll not go into the details of that. Tomorrow, as I said, we'll go into a very interesting documentary once again. And probably that is going to be on Google Meet again. Um, yeah. I mean, I'll share this presentation with you all. It's very important and it's very useful for students. So yes, I will surely share it with you. Okay, so you can connect as to which of the topics you have done, which of the topics possibly if you are doing competitive, you have to do on your own. That can be done on your own self as such. So yes, I'll surely share it. If I forget, please remind me that I need to uh, share this particular slide with you all also. Yeah, any other questions? If you have any other questions, I will answer them. If not, we should take a call that we should be stopping right now. And tomorrow, same time, that's 10 o'clock, we would go into that documentary, The Planet Earth. Yeah, if you don't have any questions, let me call it a day. Thank you very much. See you tomorrow morning.